Okay, so let's get started, and as usual let's revise what we were doing last time. If you remember, last class we were looking at memory techniques, and the memory techniques were more to do with manufacturing of memory, right. So we started by saying that where exactly in the system the memory is, and how is it connected to the CPU versus the IO devices, network interface and so on. And we saw that the memory consists of multiple dual inline memory modules, right. So this set of DIMMs constitute one bank, another set of DIMMs constitute another bank, and then we have the memory controller appearing here. The memory controller basically takes the read requests and write requests and queues them. We had seen that at present the memory handles multiple outstanding requests, right, and there is a scheduler which schedules it to the corresponding banks, and also we have a response queue where the response produced by the memory banks are stored and forwarded, right. That is the basic architecture of a memory system. And we had said that as far as a bank is concerned, a memory bank, it can have multiple outstanding requests, but as far as a single memory module is concerned, it does not, right, unless it is a rambus DRAM. And then we had discussed about various manufacturing technologies for the memory, starting with magnetic DRAM, SRAM, multiported SRAM and so on. And then we had seen the bandwidth, latency, cost and so on. And we had said that the main memory is essentially DRAM based. Of course, various improvements have been carried out on the DRAM memory to improve its performance. And then we had said that since the earlier times, once the memory chips started becoming larger, the address was split into the row address trove and the column address trove, and these were multiplexed on the same lines, on the same address lines. And then we had said that just like the main memory is DRAMs, the cache is SRAMs, and we had seen that SRAMs, they have 6 transistors, a more sophisticated configuration than the DRAMs, and therefore, here the access time and the cycle time is the same, and also you do not have to write after every read as happens for DRAMs. And then we had looked at the next improvement to the DRAM technology, the synchronous DRAM or SDRAM, which is still in some form being used in the present memory. The main idea was that to make the memory access synchronous to improve its speed of average access time. And then we had discussed about the dual inline memory modules, and we had said that nowadays you have chips on both sides of the board, whereas earlier 5 years back you had only mounted on one side of the board. We had looked at an improvement called as the rambus DRAM. We had said that the Rambus Corporation, it proposed and implemented, designed a packet switched bus. The memory module itself can have multiple outstanding requests, right, and as a result the control logic and configuration registers are sophisticated, and it appeared one time that this would be the next thing in memory, but we saw that it has some disadvantages: higher cost, higher heat dissipation. You can identify a RDRAM DIMM or a RIMM RIM as it is called, by looking at a heat sink mounted on the DIMM. So, we had said that even though it was a technically improved technology, but still it commercially it was not a success, because it did not achieve the threshold required to reduce the cost of manufacturing, and the DRAMs, the SDRAMs were improving in their manufacturing technology. As a result, almost every desktop nowadays use SDRAM based memory, but the RDRAMs are still being used in some areas where memory is very critical. For example, video gaming and some video cards and so on. We looked at the flash memory. It said that this is become very popular in the last decade or less than that, maybe in last 6-7 years, and we had said that it is actually a form of EEPROM, but unlike a EEPROM where you write a word at a time, here you write an entire block in a flash. So, it is much faster, and also the control logic is much simpler. You do not have to control at the word level, but at a block level, and therefore, it is cheaper. And then we had compared a flash versus EEPROM and had said that nowadays EEPROM is not used, right, even in unless you really require to protect some piece of data, because we had said that EEPROM you need a special system to write data onto it, whereas flash can be written just like a memory. And then we had looked at the technology of floating gate, where the charge is injected through high voltage, and we had said that very fast read time comparable to a DRAM, whereas write is milliseconds. We had looked at the multi-level flash technology, where higher capacity could be achieved by controlling the voltage on the floating gate, right. The charge that is induced is accurately injected, so that multi-level voltage can be stored on the floating gate and also read. But we had seen a shortcoming, that the number of writes is restricted, whereas reads are unlimited. As a result, the flash memory is becoming very popular, where reads are more than writes. For example, an iPod, right? You might have heard of an iPod, or might have been using iPod, which just plays music, right? You don't update it very often. You don't store music each time you play it. So, earlier the iPods were using micro discs, but that has larger power dissipation, right, that is a magnetic memory, and also larger weight and volume. Whereas, now that the iPods use flash memory, the power dissipation is small, and you might have seen the latest iPods, which are really thin and small, right, thinner even than a cell phone, right, 1/4 of a cell phone. So, that has been possible by flash memory, and the main idea is that iPods read more than they do writing, whereas as far as the question of replacing the hard disk of a computer with a flash memory, it is still not possible. We do not know what would happen in future, but till now it is not possible to replace a hard disk with a flash memory, even though the costs are comparable. Hard disk is of course cheaper per gigabyte, but still it has not been possible to replace the hard disk with a flash memory, simply because flash memory with large number of writes can go bad, whereas hard disk does not, right. So, then we had looked at virtual memory, and we had found that the page table entries can be enormous in the modern systems, and some of you said some 64 terabytes, is it? How many 64 tera pages are required and to store the page table, but you can't really store a page table that long because it will be too much of a memory overhead, right? And we said that if you have a single page table, you have no other option but to store all of them, and as a result normally a hierarchical page table is used where you have large number of page tables organized hierarchically. And we had also posed this question that how does to access one word from the main memory, if you have to read the page table once and the second time is to access the word itself, would be too much, right? But said that the TLB eliminates the need to access the main memory for getting the address most of the time. The physical address we can get from the TLB 99.9 or so percent of the time. We looked at the contents of the TLB, and then we were discussing about the alpha 21264 virtual memory, and we had said that the large number of page table entries is a matter of concern for any modern computer. And as a result, alpha tries two things. One is it uses segmentation. One of the objective of the segmentation is to reduce the size of the page table. The other is of course to protect the kernel and so on. We had said that for the segment 2 or the kernel segment, no memory management is used. The kernel is resident all the time. Why was that necessary? What if the kernel itself is, the memory management applies to the kernel itself? What would happen? Can anybody say that? What about the code that does memory management itself? If that itself is not available, how do you run those code? Things like that. So, there are various kinds of complications. As a result, the kernel is resident permanently, and then we had said that the user processes live in segment 0 and the segment 1 uses page table, and at any time only portions of the page table is resident. That has been possible by a hierarchical page table arrangement. It actually uses a 3-level hierarchical page table. I have not really made the slide for the hierarchical page table. I will just use the paper to draw a hierarchical page table. So, the physical address is 48 bytes are used. We had said that only 48 bytes are used, and 2 bytes are used to identify the segment, right. The higher order 2 bits are used for segment identification. And then the rest is divided into 3 parts, and of course, we have the page offset, and this is 2, and this is the page, these are 12 each, 12 bits each. So, 12, 36, 48. So, the page size is 10 bits, 1K pages. Now, the first level here, the page table base register is used with this one to get the first page table here, and we had said that it had 64 entries, is not it? and now depending on the page table it points, the next level is obtained by using the next set of 12 bits, and that will point to another page table. And now the next set of bits is used to get the next page table, the third level page table, which contains the physical address. But how many page tables will be there? Can anybody tell? No, not 3. How many page tables will be there? See, we said that if we do not use a hierarchical one, we will have only one page table, but here in this hierarchical one, a single page table exists for if we do not use a hierarchical scheme, where all details of the pages are available. But what about in a hierarchical arrangement like this? How many page tables will be there in this level, level 1? Yes. What about the next level? So, for each of these you will get a page table, is not it? For each entry here you will get a page table at this level. What about this level? For each entry here you will get 2 to the power 12 entries, right, not page tables. Then you will have to find the page tables there. Does that appear all right? How many page tables will be there? Can you find out? So, just see that all these page tables do not have to be resident at the same time. The number that you get 1 here, and he said that corresponding to each entry here there will be a page table. The question? Yeah, see, we were trying to say that if you have a single page table, right. So, this is scheme 1. Okay, let me just write this as the scheme 1 and this as the scheme 2. The scheme 1 is a single page table. Okay. Now, the single page table, I was saying that you can't apply memory management to it, you can't make part of it resident, because once you take a offset with PTBR, right, it has to be there, otherwise how do you get it, isn't it? Whereas, we are saying that to store only part of the page table, considering that the page table is very large, we can't store all of them, or at least very difficult to store all the entries in the page table. We are using a hierarchical scheme, and then we are splitting into small page tables, large number of that. And then I asked you, posed a problem to you to find out how many page tables will be there, and then some of you said that at the top level there will be 1 or something like that, and then for each entry here there has to be a page table for each one here, each entry in this page table there will be separate page table at the next level and for the next level. So, the page tables will be like this: at the top level there is 1, and then you have as many page tables at the next level as there are entries here, right, and for each of them you have a separate page table, right. That is a hierarchical page table arrangement, and I posed you a problem to find out how many page tables, individual small page tables will be there. And then I said that in this arrangement you do not have to store all the page tables at the same time, otherwise that will be a large overhead. You can only use those page tables which are currently being used.
At a time only 3 page tables are available.
Not 3, there can be many. For example, at this level, let us say 5 or 6 page tables or maybe 100 page tables, small page tables are being recently used, right. At this level, let us say 1000 are being recently used, you only store that much. So, just think of it, not a very complicated problem, just think of it. So, we had said that the page table number of entries in a page table, to manage that is a challenge, and alpha manages it by using segmentation, and it does not use any memory management, and as a result no page table entries exist for the kernel segment. Kernel is always resident, whereas the memory management, the virtual memory, is used for the user processes and the page table itself, the seg 0 and seg 1, whereas k seg there exist no page tables, right. And again it uses a hierarchical scheme to reduce the number of page tables that need to be stored, right, the size of the page table. So, I had in the last class I had asked you to find out what happens in Windows and in Linux, and to make a survey, the literature, papers available, the documents available on the net, and then submit it, and I would consider that as a bonus mark, right. Please find out how is the page tables managed in Windows and in Linux. We were just talking about the alpha 21264. And then we okay, let us summarize the main memory optimizations. We had looked that the technologies that are being used is wider memory, interleaved memory, and we had looked at DRAM specific optimizations like SDRAM, DDR, SDRAM, and so on. Now, let us have a case study just to see what happens in the memory system of Sunfire 6800. It is not a very recent computer, but let us see what happens here, maybe 5 years old, right, 5-6 years old, the Sunfire 6800. So, let us look at the L1 cache. The L1 cache is on chip. There are two L1 caches, the data cache and the instruction cache. Sorry, I think the data cache is 64 KB and the instruction cache is 32 KB. I have written it wrongly. The data cache is always larger than the instruction cache. Just make a correction here, I have written it wrongly here. The data cache is 64 KB, instruction cache is 32 KB. The block size used is 32 bytes, 4-way set associative, even though we said that all L1 caches are direct mapped, but they use a different scheme here, possibly because it is an older computer. Please find out what happens in the modern computers. Write through, but no write allocate. I hope all these terminologies are clear to you. We had discussed it extensively. The L2 cache is a 8 MB unified cache, but only part of the L2 cache is resident on the processor. The tags part for the L2 cache is on chip, whereas the data part is outside the processor. So, the total size of the L2 cache that is resident on the chip is 90 KB, comparable to the L1 cache. The resident part of the L2 cache is comparable to the L1 cache. It uses a write back with write allocate, whereas L1 cache uses a write through with no write allocate. Why is that? Can anybody answer this question? That why is that the L2 cache is write back with write allocate, whereas L1 cache is write through with no write allocate?
Right variable is very less for precision, but whereas in L2 that is
Exactly. I hope everybody has got the point that he is trying to tell. He says that writing to L2 cache is less expensive, whereas if you use a write through at the L2, the memory traffic will be too much, right, latency will be too much and memory traffic will be too much. It uses a 2 KB write buffer. We know what is a write buffer, and it supports outstanding memory accesses. The memory system supports outstanding accesses, up to 15 accesses, up to 15 outstanding accesses are supported. The memory system is virtually indexed and physically tagged. The cache is virtually indexed and physically tagged. I hope all of you remember what is that. So, here the advantage of using a virtually indexed physically tagged cache is that you start the cache access by using the virtual address, and by the time you locate the entry here, you have completed the virtual to physical translation, and you can compare the physical tag with the entry in the cache, because we had said that a virtually indexed virtually tagged one would have many complications, right? Because can anybody say what are the complications with a virtually indexed virtually tagged cache? Anybody remembers? We discussed about it.
The protection bits that are
Okay, one is protection. How do you handle protection? Yes, but that can be easily circumvented. We had told about that. But what are the main problems here?
context switch.
Yeah. So, different processes, when they change, when there is a context switch, the same virtual address might refer to different physical addresses. As a result, with the cache you would have to store the process ID, and not only that, sharing of memory among the different processes is again poses another problem. We had talked about the aliasing problem and so on. So, a virtually indexed virtually tagged would be too complicated, and as a result a virtually indexed and physically tagged cache is used. It uses two TLBs, even though we have been so far talking about a single TLB. It uses two TLB, a 16 entry fully associative cache and a 128 entry 4-way set associative cache, just to optimize the access time to the TLBs. Both data and instruction prefetch is used. There are separate buffers, a data prefetch buffer and a instruction prefetch buffer. The data prefetch buffer, up to 8 data prefetches, which can be done both by hardware and software, are supported. At any time there can be 8 prefetches, and these are done both by hardware and software. We know how it is done by hardware and software. And if a request to the memory, a load is request is hit in the prefetch buffer, then the next load address is also prefetched by the hardware. And there is a smaller instruction prefetch buffer, just 32 bytes. And on an instruction cache miss, two blocks are requested. One is for the instruction cache itself, and the other is for the prefetch buffer, because we had said that the instructions are mostly accessed sequentially. So, this makes sense here. Get two blocks, one for the instruction cache itself and another for the prefetch buffer. So, we had made a case study of a Sunfire 6800, and I said that this is an older processor. So, I would request you to make a case study for the modern processors, the Pentium 4 and the Athlon processors, and you can make the case study and send me in the same format as this one, as the slides are, the slides that we have made here. It should be in the same format, and those who do it well, there may be multiple of you, of course, we will consider them for bonus marks. I have just made one. I did not have time to make a case study for the modern processors, the memory system for Intel Pentium and the Athlon processors. Please send it to me. It will also be useful for me, because in the next batch of the students we will use that. In addition to the Sunfire 6800, we will use the Pentium and the Athlon case studies. So, what kind of caches are used, what kind of associativity, block size, memory management, prefetch buffer, and so on. Now, let us address one problem before we conclude the memory part, the memory technology. Actually, we are hoping to complete this part in the last class itself, but somehow we are not able to complete that. We are hoping to start the multiprocessors. So, as soon as we complete this part, we will start that. So, let us look at another issue about the memory. The issue is consistency of cache data. See, the problem is that data is the same data is there in the cache as well as memory, because after all the data is fetched from memory to the cache. So, the same data is resident in the memory as well as cache, is not it? But when the CPU is the sole accessing unit for the data from the cache, then there is no problem of inconsistency. But the thing is that in addition to the processor, the I/O also can change the memory contents. I hope you remember the figure that we had discussed, the architecture of the modern computers, where the I/O is performed directly with the memory system. So, most modern systems, the I/O occurs directly to the main memory. As a result, there is a problem of data becoming inconsistent. The one that is present in the cache is different from the that present in the memory, because the memory was updated by I/O and not the cache. Does that appear okay? Why the inconsistency arises? Does anybody have difficulty with why inconsistency arises when we have cache data and the I/O occurs directly to the memory? Everybody is fine with that, is it? Okay, good. So, if it was a write through cache, there will be no inconsistency with I/O writes. I mean, you are writing to the I/O. I/O writes, I am meaning that you are writing to the I/O, because the cache and the memory are always up to date.
So in so in write through cache, whenever we update the cache, then simultaneously we update the memory.
Exactly, yes. When you update the cache, you also update the memory, yes.
And I/O devices are directly accessing.
I/O devices get the latest data that is also there in cache. If it was a write back, the problem would be that the latest data is available in the cache, but not in the memory.
So I/O devices accesses memory through the DRAM
Yes.
and updates the memory.
Yes.
But in that time, cache may not be updated.
Exactly. So, see the second line, the last line here, we are just talking of IO, IO writes, but what you are saying is IO reads. So, IO read problem will be there even with a write through cache, but what I have written here in this line is that for write through cache, the IO writes will not cause a problem. There will be no inconsistency if we use a L2 write through cache, because the cache and the memory are always up to date. Whereas, if it was a write back, the latest information may be there in the cache and not in the memory, and if the I/O occurs with the memory, then the output would be improper, is not it? So, the problem with the write back L2 cache, I hope that is clear, but unfortunately the L2 cache is always write back. Do you agree with that? The L2 cache is always write back, it is not write through. Anybody disagrees with this? Okay, good. Everybody is agreeing that the L2 cache is always write back, and as a result, it does not help us to prevent inconsistency even in writes. Reads, there will be of course inconsistency. So, this is a big problem. How do you solve it? The modern computers, they use many approaches. One is to use some software or hardware techniques that can guarantee that no blocks which have been marked for I/O are present in the cache. So, if something is to be, some block is to be read or written, either a hardware or software technique can be used to ensure that the same block is not present in the cache, it will be marked invalid. If a block is marked for I/O, that block will be marked invalid in the cache. The second solution many computers use is that I/O always occurs to a buffer marked non-cacheable, and then it is accessed later from that buffer by the cache, right. So, this will be copied to its proper place and then it will be accessed. So, the IO occurs to a special buffer which is non-cacheable. The third technique is a hardware solution. It will check the IO address to see if it is in the cache. If it is in the cache, then it will be marked invalid, right. So, many computers use some of these three solutions. So, does that appear all right? So, we have come to a end of the memory technologies, how the memory performance has been improving, and we had started by looking at the performance that is required from the memory hierarchy should match with the speed of the processor. Otherwise, there is no point in making the processors first if we can't supply the data at the required rate. And then we had tried to find out, analyze how the memory performance can be improved, and then we had said that the hit time, miss rate and miss penalty, these are three separate parameters which can be optimized, and we had seen dozens of techniques that are being used to improve the cache performance, right. And we said that what we discussed is non-exhaustive. There are many more techniques that are being used, and some of the techniques are actually proprietary, not given out by the manufacturers. And then we had looked at the manufacturing technologies, DRAM, synchronous DRAM, the RDRAM, rambus DRAM and DRDRAM and so on, the flash memory and so on. So, now we will start discussing about the multiprocessors. So, let us look at the thread and process level parallelism. First, let us have an introduction to multiprocessors, and then we will see the various issues that are present in the multiprocessors. Because as you might be aware that multiprocessors are being used in the desktops also. The dual core and quad core processors have been introduced, and the single core processors have been phased out. From now on, any machine you buy, whether you are buying a desktop or a server, it is actually a multiprocessor, right. So, let us see why was it necessary to have multiprocessor, because it appeared that we are doing all right to improve the performance of a single processor. There are various techniques that were used. Can't we carry on with that? Why do we need a multiprocessor? Because as you will see that multiprocessors have several problems that need to be overcome. So, does anybody have any idea why is it that we can't increase the performance of a single processor, or why can't the chip manufacturer, the processor manufacturers can't use a single processor anymore? Why are they going for multiprocessors? Does anybody have any idea?
Clock speed is going to limit.
Not really. Clock speed can still further be improved, but let us see what are the issues. Let us try to find out that answer in next couple of slides. So, we had so far seen that the initial computer performance improvements were achieved through innovative manufacturing techniques. We had seen that the vacuum tubes gave way to the semiconductor, discrete semiconductor devices, transistors and so on, integrated circuits, very large scale integration and so on. Those are the manufacturing techniques. But in later years, most improvements came from exploitation of instruction level parallelism. We know what is instruction level parallelism, and we had said that the advantage of instruction level parallelism is that it is invisible to the programmer. The same C programmer, Fortran programmer, whatever, you run it in the same way as far as the programmer is concerned. It is compiled and run without any special effort by the programmer, right. The instruction level parallelism exploitation is transparent to the programmers. Do you agree with that? And we had said that pipelining was the first thing that was used, and then we had looked at dynamic instruction scheduling and superscalar execution and so on. And both software and hardware techniques were used. We had seen the compiler techniques that were used and the hardware techniques that were used: pipelining, dynamic instruction scheduling, out of order execution, VLIW, vector processing, and so on. We had looked at all these things. But the thing is that ILP now appears fully exploited. Further performance improvements from ILP appears limited. Not only that, we will see a further problem why we need multi-threading and multi-core processors. So, the way to achieve higher performance appears to be exploitation of thread and process level parallelism. Here the idea is that we exploit parallelism existing across multiple threads or processes, which cannot be exploited by any ILP processor, because the ILP simply takes the instructions that are supplied to it. It can't identify which is a thread, which is a process. It can't. It just keeps on executing the instructions. But many modern applications, whatever you can think of, you can identify there are multiple threads in that. For example, a banking application, different customers have come and they are trying to withdraw money, deposit money, query balance, and so on. These are their individual transactions, and the transactions can be executed in parallel. You can think of each transaction as a thread for a user. So, we need to just reflect back little bit on the processes and threads, even though you might have done it long back in your operating system course or wherever. So, just to recapture the very elementary things about a process and threads, hopefully you have not forgotten about this. We will just spend a second here. A process is a program in execution, and modern applications normally consists of multiple processes, whereas each process might consist of one or more threads. Then what is the difference between a process and a thread? The difference is that the threads belonging to the same process share data and code space, whereas different processes do not share their data and code space, right. This is a pictorial representation here. This is a process. Each process has its code, data, and other files which are open and being accessed, registers and stack which are private to this process, and it has a single thread of execution. Whereas we can create multiple threads in a process. So, here the code, data, and files, open files, are common. They can be accessed by any thread here, whereas each thread has its own separate registers and stack. But how can threads be created? Can anybody tell? The threads can be created by using popular thread libraries. I hope many of you would have created threads. For example, the pthread library supported by the POSIX compliant operating systems, the Win32 threads, the Java threads, and so on. But just one point here, that how is a user thread different from a kernel thread? What is a user thread and a kernel thread? Let us spend a minute to find out what is it. Originally, when threading was not supported by the processors, I am talking of about a decade back, when the processors did not support threading, the thread management was done in the user space. The user threads are supported and managed without any kernel support, right. So, as if you are writing application and you are managing your own threads, and these threads are invisible to the kernel, and as a result, if one thread blocks, the entire process blocks, and as a result there is a limited benefit of threading. But let me just ask you one question here, that what are the advantages of threading? Why is it threading is a good idea?
It's produced on a parallelism already.
Let us assume that see, his answer is that the multiple threads that are created can be executed in parallel by the processor in a multi-threaded processor, right? But let us assume the processor is even not supporting multiple threads. Still, will it be beneficial to have multi-threaded programs? No, that happens for processes, not for threads. So, can anybody answer this question? That
multi-core programming and time sharing environment, context switching is more.
Yes.
To avoid that context switching overhead time.
Okay. Yes, I think he is on the right track. See, his answer is that thread creation is much more efficient than a process creation, and also thread switching is much more efficient than process switching. When you switch a process, you have to get its context, right? Whereas for thread switching, they share the context, you do not need to change the context. So, thread switching is much more efficient than process switching. Even if one thread blocks, the other threads can continue without incurring a context switch overhead, right. So, I hope that point is clear. Now, let us look at what is a kernel thread. A kernel thread is supported and managed directly by the operating system. So, you request to create a thread by using a thread library, and then kernel creates lightweight processes or threads called as LWPs. And most of the modern operating systems support creating kernel threads. Windows, Solaris, Linux, Mac, whatever you can name, they all support creating threads. So, these are the benefits of threading. One is responsiveness, as we were just discussing, that threads share code and data, and as a result thread creation and switching among threads is much more efficient than creating a process or switching among processes. For example, in Solaris the data is available. Creating threads is 30 times less costly than creating processes, because you do not have to create separate code space and data space in the memory, right, it is already available. So, creating a thread is 30 times less costly than processes, and context switching about 5 times faster than that of processes. And also, in the modern processors, we can have multiple threads executing in truly concurrent manner. We will just discuss this topic in the subsequent slides. The processors that support concurrent execution of threads, which are called as simultaneous multiprocessing, multi-core processors, multi-threading or simultaneous multi-threading or hyper-threading, symmetric multiprocessors, multi-core processors, simultaneous multi-threading, which is also called as hyper-threading. So, we will look at each of these techniques. Now, let us see the processor support that is required to exploit thread level parallelism. In pure instruction level parallelism, the execution unit utilization is about 20% to 25%, that is experimental data. We had seen that in modern processors, we have multiple functional units, floating point units, integer units, IO units, right, and so on, and their utilization is only about 20% to 25%. What is the cause for this? The problem is that there are various kinds of dependencies between the instructions, and as a result the utilization is limited. Not only that, what about cache misses during memory access? We had said that the speculative execution and so on, they end once there is a miss in the L2 cache. We had discussed about that. So, due to these problems of cache misses, the various kinds of dependencies, we can't keep the various units, the functional units in a processor busy, and it is as low as 20% to 25%, and it would be extremely rare to come across a program that can keep the units even reasonably busy. definitely not for the benchmark programs, and even if you want to write a program that will keep these units reasonably busy, it will be very hard for you. The problem is that in pure instruction level parallelism, at any time only one thread is under execution. So, the utilization of execution unit can be improved if we have several threads under the execution at the same time. These are called as active threads in the Pentium 3 processor. We have several threads, but at any time only one is under execution. Whereas the modern processors, the hyper-threaded processors, symmetric multiprocessors, the simultaneous multithreading and the multi-core processors and so on, here the several threads are execution at the same time. See the difference here? Here at any time only one thread is executing, and once that blocks, the other threads are taken up for execution. Whereas in the other case, we have several threads simultaneously executing. So, threading can help improve the performance to a great extent, but we are not saying here that threading can be achieved only using multi-core processors. We are not saying that. Threading has been was being used or has been still being used in a single core processor also. We will see first that one, how in a symmetric multiprocessor, in a simultaneously multi-threaded processors called as a hyper-threaded processor, how is multiple threads are under execution in a single processor. And then we look at the multi-core processors where there are separate processors available, and each of these processors called as a separate core again uses separate multiple threads. Each of the core executes multiple threads. We look at these techniques. So, we will just stop here and then continue from here at this point onwards.